Hello, this is Teach Nichols, and this is an AP Physics 2 review video on common mathematical relationships. The essential question is, how can we use mathematical relationships to predict how changing one variable will impact other variables in an experiment or from a graph? You may remember from your first physics class that mathematical relationships are incredibly important in physics, because the goal of physics is to be able to explain the past and predict the future, and these mathematical relationships are what gives us the power to do that. So in order to predict the future, we need to figure out how changing one variable in the world will impact other variables around it. Any connection between two variables is known as a relationship, and these relationships end up being the building blocks of equations. In general, it is often helpful to just know broad strokes if increasing one variable will make the other one go up or down or not change. But the little nuances, with advanced physics, you really want to be able to tell how much changing one variable will change the other. And this how much is not a number, it's a ratio. It's by double, by triple, quadruple, whatever it is. That's what we're sort of interested in moving forward into more advanced physics. I don't want to fail to remind you of the most common mathematical relationship, which is no relationship. It means that changing one variable has no impact on the other variable. And this sometimes happens in like a physics experiment as well. You're expecting something to change other things and it turns out it doesn't. For example, there is no relationship between the mass of a pendulum and its period. Most people think that a heavier pendulum swings faster or something of that nature, but it turns out that the mass of the pendulum has no relationship to how long it takes to go back and forth. Two people sitting on a swing, no matter how big or small they are, end up swinging back and forth with the same frequency regardless of their mass. Maybe that's something you've experienced before. So that would be a no relationship. Pendulums, incidentally, not in this class, but the period depends on the length of the swing and the gravitational pull of the planet it's on, but nothing else. If you have a data set that is going to show you a no relationship, it will graph out on a scatter plot as a flat line, a flat horizontal line or vertical, depending on which axis you put your variables on. And what this line tells me is that no matter what is happening to the independent variable, the dependent variable value doesn't change. There's actually still a lot of useful information you can get off of this graph. For example, the slope of this graph is 0. That's by definition true for a no relationship graph. But this tells me that as the mass of the pendulum increases, if I put more mass on my swing, the period is not going to be changing. You also can learn something from the intercept of this graph, which in this case is 7 seconds. That tells me that for the pendulum that I'm looking at on the planet that it's on, it's always going to take 7 seconds to get back and forth, regardless of the mass that you put on it. The other piece of information you sometimes can get out of graphs that's useful has to do with the area under the graph, like how much physical space is between the x-axis and the graph for any y-coordinate. In this particular graph, that's not a useful piece of information, but I just wanted to bring it up because you will be using that at other times. Linear and quadratic relationships sometimes appear in the same bucket because they are examples of positive mathematical relationships. This means that when one variable goes up, the other one is going up. And the slopes of these two kinds of scatter plots or trend lines on graphs are always going to be positive. A couple examples of these positive relationships. If you have a spring and you're stretching it, the amount it stretches is going to be linear with the amount of mass that is hung from it. And the distance an object covers is going to be quadratic with the acceleration of the object. So the greater the acceleration of an object, the greater the distance is going to cover. If you have a pure linear relationship, not quadratic, then what happens when one variable doubles is the other variable is going to double as well. The lovely thing about this is it makes a trend line on a graph that is a straight line. And so you will see the graph to the right shows the amount of stretch of the spring, has a straight line trend line with the amount of mass that you hang. This is actually our favorite kind of graph because there is a ton of useful information. For example, the slope of this graph is constant and positive. In this case, it tells delta y over delta x, or how much the length is changing for every additional 1 unit or 1 kilogram change in the amount of mass hung. really easy to find. We've hopefully been finding slopes of lines for a long time, and so that is a piece of information that is readily accessible from a linear graph. You also can easily find the y-intercept or the x-intercept if that was relevant. In this case, it's 0 centimeters. What that means physically is that when no mass is hung on the spring, it doesn't stretch, which probably should make sense if you think about it. You also can pull information from the area under linear graphs pretty easily. You could find the area because it's a triangle, right? So for any y distance along that axis, if you kind of cut it off and imagine the shape of that triangle, calculating geometrically the amount of space under that trend line actually can give really good information. In this problem, it's actually related to the amount of energy that the spring stored, which is something that physicists and engineers need. You're not expected to know that going into this class, but just realize that we can find the area under linear trend lines using geometry, and that information is often really helpful. So the other positive relationship graph that we're going to start seeing in this class is called a quadratic relationship. In a quadratic relationship, when one variable doubles, the other will quadruple. And that's because instead of being x versus y, it's x squared versus y, right? If you double something and then square it, it quadruples instead of doubling. You'll know you have a quadratic relationship if you plot the data and instead of being a nice straight line, it actually sort of zooms up, right? In a constantly positive slope, but it's changing and becoming more steep as time goes on. I hate it when I see this kind of graph. Like, this is not that useful. Other than taking individual data points off it, you can't really find the slope of this graph without calculus. You can't find the area under this graph without calculus. Those things are constantly changing in ways that are a little bit more mathematically hard to handle. So what scientists and physicists will do is something known as linearization. We take any graph that's not a straight line and we're going to find a way to make it into a straight line. Usually what we're doing is we take the data set and we do a little bit of math on the variables before we graph them. So in this case, if instead of graphing acceleration and distance straight up, we take the distance and square it, okay, then when you graph this, it comes out to be a nice straight line with an easily defined slope, intercept, and area. So this is called a linearized graph, and it shows a quadratic relationship because you can see that one of those two variables there is squared. In inverse and inverse squared mathematical relationships, you will find that increasing one variable decreases the value of the other variable. One example of an inverse relationship is gas pressure having an inverse relationship with the volume of a container. So if you could take a container with gas and you squish it, right, the volume becomes smaller, the pressure inside that container actually goes up. An inverse graph will look like the graph on the left. It has a constantly changing negative slope. It has no intercepts, so you can't even get intercept information, and finding the area under an inverse graph also requires calculus. So it's a pretty annoying graph to get on your data set because there's not much you can do with it. Just like with the last example, what you're going to want to do is linearize this graph or turn it into a straight line so we have something with a very easily defined slope, intercept, and area. But the way to linearize an inverse graph is a little bit different, right? Inverse means reciprocal. So what you need to do is to, instead of graphing pressure and volume, you need to do a little math on one of those variables first. In this case, I did the math on volume, and I took the reciprocal. I did 1 divided by all of my volume data points. When you graph this new data set, pressure versus 1 over volume, you get a nice straight line graph with all sorts of benefits and perks. So that on the left is an example of an inverse data set, and on the right, what you would do to linearize an inverse data set. One very important example of an inverse squared relationship is the force of gravity, which has an inverse squared relationship with the distance between the two massive objects that are pulling on each other. An inverse squared graph resembles an inverse graph quite a bit, actually. It still has no intercept, and the slope is constantly changing, and an area that you need calculus to define. But it's a little bit steeper. It's a little bit more of like a right angle there if you can see it on the graph. So if you recognize that in a data set, it's possible you're dealing with inverse squared. Linearizing an inverse squared graph is pretty much the same as the other ones. This time you need to do 1 divided by the x or independent variable squared, and that should create a straight line graph for an inverse squared relationship. Okay, hopefully this video has been a good quick review for you about how we can use mathematical relationships to predict how changing one variable will impact another. Thanks for watching.